everyone. Thank you so much for coming and giving up your time. I know everyone's preparing for exams, so we're very happy to have you all today. We have an amazing presentation prepared for you by Professor Evan Keane today. So yeah, if you guys have any questions, you are free to ask them during the presentation, or if you want, or you prefer, you can keep them towards the end. So we're going to have a little Q&A section at the end. So yeah, without further ado, I'm going to let the professor introduce himself, and yeah, I hope you guys enjoy the talk.
Hi everyone, thanks for inviting me. Thanks for clapping before I do anything. They asked me to introduce myself for a minute or two. So I'm Evan. You can just call me Evan. So I've been working here since January, so I'm kind of new. I've almost done one cycle, so I've almost seen it all at once, but still very much don't know how everything works. I recognize some of you from courses I've taught, and yet you still invited me to talk. So, joke's on you. So I'm from Galway. I did my undergraduate there, and then I went to, I did part 3 in Cambridge, and I did a PhD in Manchester, and then I traveled around the world working in various places, and was in, before I came, I Brexited in 2020 to come back to Ireland, and pretty happy to be working here. Okay, and I am a radio astronomer. Part of the perks of the job we're working here is that I'm director of a telescope, a radio telescope that is in Birr, which is like smack bang in the middle of Ireland, which explains the Birr in the title. I'll tell you what that is, because I have to give you Radio Astronomy 101. Sorry about that. But when I arrived here, they hired me to be professor of radio astronomy, and I said, "Oh right, how many radio astronomy courses are there?" And they said 0. Like, oh, okay, right. So that's going to change. But I have to. But that's why I'm giving you guys a crash course on radio astronomy. You know this guy? This is Maxwell. And this is where I say that Maxwell's equations are symmetric in time. And that's sort of the key underlying principle of how an antenna works. I guess you know that if you have some electric charges moving in a wire, that it will radiate some light. Because of this symmetry, it works the other way as well. So that if light is incident upon a wire, it will make some electrons start to move. And that's how an antenna works in transmission or reception. So if you get a telescope like this, you guys are probably all born this century, so you don't remember things like this being used as antennas on television, but I do. This is any old piece of wire. It's good. It works as a telescope. If I want to see the sky using that telescope and say there's something over there, I want to point my telescope at it, the light coming in will cause a little bit of movement of electrons in the wire. And if I connect a voltmeter to that and measure the voltages, you'll find that the voltages oscillate in time the same way as the electric field. There's a big derivation of that you guys might see in your studies, but just believe me for now. The reason I say voltages is because the voltages are directly proportional to the electric field coming in. And so when people say, oh, we see radio waves, what they really mean is we see the voltages induced in a wire due to the electric field, but they're kind of proportional and we know what the constant is. So that's what they mean. Right? So, but it's measuring, it's electronics, right? It's a sort of an understandable thing. Or something you guys come across in labs, even though you don't come across radio telescopes as such. The thing is with this radio telescope, though, is it's not very good. This was the view from my previous office before I came here. Now I see a rugby pitch. And I have a nice office, to be fair, but somebody was, some established Trinity person said, well done, Evan, you've got a lovely office with a lovely view. Like, oh yeah, this is my previous view. And so the thing is with that little telescope, the idea is if only there was some way you could sort of build a giant big bucket and collect loads of light and then sort of focus it onto your little antenna, then it would be much better, much better. And that's it. That's how radio telescopes work. Simple enough, right? Now, I've glossed over a few complexities. If you've done thermodynamics, you know that the electrons in a wire are just moving anyways because they have temperature. Right? Temperature is just things moving. So we cool it down. So if you climb up on the top of this thing, which is really scary, but you can do it when it's pointed up, you'll hear, cooling pumps going, liquid nitrogen canisters and stuff. Keep it as cool. Keep that kind of thermal stuff as low as possible. And there isn't just one coat hanger type thing. There's two that are usually like this to get two polarizations. And a lot of the effort goes into mechanical engineering of this thing because it weighs a lot of tons. This particular one is 76 meters across the dish, and it's made out of battleship bits, old battleships. So yeah, I think this thing on the side is like a gun tower or something. Yeah, well, it's made out of lots of steel. Whoops! Oh, I don't want to go to the final word. Sorry about that. I love how that's possible. Just go to the end with one click. Okay, so this is really what a radio telescope, radio astronomy looks like. Something like this. Right? You get a big telescope, and actually, that collects loads of light, goes onto your wire. Great. You collect the voltages, and then you send the voltages into pretty big computer, and you try to find the needle in the haystack in the data. And so you do the detective work on the computer. Okay. But yeah, so that's good. And if you have a telescope like this is built in 1957. If you have a telescope like that since 1957, you sort of you do it all. You find everything you can find, and you think, oh, I wish I could see a bit further. I might build a bigger telescope. And there's loads of these dishes all around the world. These are, this is a gallery of some of them. The one I showed there is, I don't know if you have a pointing thing. It's that one there, the smallest one in the middle. Right, so there are bigger things than this. Okay? That's the biggest one in the world there. That's called FAST, the 500-meter aperture spherical telescope. So it's 500 meters across, half a kilometer. That's in China, in a sort of a natural valley between some mountains. Lovely place for a radio telescope. The only thing is, when you have a half a kilometer long dish of metal, it's very heavy, it can't, it gets to the point where it can't move. And so this telescope doesn't move. And so it basically looks straight up. Okay? And the sky moves. Okay, that's convenient. So we can see a strip of the sky. Right? And in that strip of sky, this telescope's brilliant. But what if you want to look over there? It's no good, right? And this is kind of a natural limit of building these big dishes. And there's been examples that you may have heard of big dishes falling to bits, collapsing under their own weight. That's happened with a couple of, so the Arecibo telescope there, the 305-meter one, that's gone. It collapsed like a couple of years ago. I won't get into, seeing as it's being recorded, I won't speculate as to why that happened, or why it was allowed to happen. There's a 100-meter telescope there in Greenbank. There was a previous telescope in Greenbank that collapsed as well. It's hard to do this. It's hard to do these telescopes. But you're kind of getting to the limit of engineering, right? And so what you could do is you say, all right, well, this little coat hanger I had at the start, it's not very good, but it's really cheap. And it's really easy to make. Maybe I'll just get 1 million of those. I'll get 1 million of those, and I'll just combine them, and I'll spread them around. I'll combine them electronically. And so now this box that says voltage is doing a lot of work. Combining the signals to make one telescope that is, synthesized, being a very big thing, that's a lot of work, a lot of computing. And so the computing detective work becomes like, one of the most difficult problems you could do in any field. But the telescope can point anywhere, and it's modular, it can be expanded, and computing infrastructure is growing at much faster than our ability to build big dishes. It's flexible in a lot of ways. So one practical way is that, so this is the LOFAR type telescope, so like the one in Birr. Though if you look at them, they're just a bunch of wires in a field, but they can look over there, and by a software command, they can instantly look over here in one clock cycle of a computer. The Lovell telescope that I showed you, that's, I don't know how many tons, I think it takes 24 minutes to do a full rotation, or a 360 rotation, because it's so heavy. You can't just whiz these things around. That's a lot. That's just one of the many efficiencies you gain. This is me in Birr, in my natural habitat, amongst the antennas. Feeling the radio waves bathing me. So this is one of the types of antennas that we have in Birr, of which there's a field full of them there. But you can see that they're just wires. Is there any pointing type thing? There's nothing the same. The mouse. Oh yes, okay. So can you see this line here? That's a wire. Comes out the other side. That's it. It's just a wire. And then there's another one at 90 degrees. Just another wire. This black thing here is just a bit of plastic to keep it safe. This is like a brush for sweeping the floor, right? Up here is the most expensive bit. There's a low noise amplifier. And then the signal goes down this brush under the ground. And under the ground, there's just a web of fiber optic cables between all these. It goes into a shipping container full of computers. It combines these signals together. But here is very simple. So that, I was standing over in the field there where it says LBAs, low band antennas. There's two different types of antennas. So there's the high band antennas. They look at different frequency ranges, low and high. The shipping container full of computers is there. So that's a shipping container that you might see down in the port, repurposed for nerdy things. And this whole, I don't know if you can see it there, but this whole ground has been lifted up a lot so that we can put cables in there, amongst other things, so that we can make sure it doesn't flood, things like that. So that's a view from a hot air balloon, actually, not a drone, in Birr, in the grounds of Birr Castle, where this happens to be. And so all of this data goes underground here, gets combined here, and sent over into this building over here, which I've labeled control room, but used to be a sheep shed, but now has a lot of expensive computers in it and no sheep. And we do a lot of science in this, here. We also have a dedicated connection that goes back to the core of LOFAR, which is in the Netherlands, from there as well. Because Birr is just one of 54 stations spread across Europe in this European scale telescope. So Birr being the most westerly. I've said 52 plus 2 because there's 52 working, and there's 2 that are in the middle of being constructed. So this is it's a modular thing, right? So if the ones being constructed are in Bulgaria and Italy. And if Bulgaria and Italian astronomers say, oh, I'd really like to join LOFAR, and they write a proposal to their government and they get some money, then they just get one. You can just add it on. If you build a really big dish and you get a little bit more money, you can't sort of make the dish bigger retrospectively. So that's nice. There's a lot of dots in the Netherlands because there's a lot of stations in the Netherlands. That's kind of the core of the network. This is a view. This is a satellite image looking down at the center, the very center of the array in the Netherlands. And you can see these are high band antennas, which you can see, and each one of these little dots are just those wires. Right? those dipole wires. And in the center, it's very dense with these antennas. And as you can see, it's a very artificial, well, very Dutch landscape, right? God made the world, but the Dutch made the Netherlands. Okay. So that's kind of how the radio telescope is and kind of how it works. But I want to get across to you, this is a big data enterprise. Very big. Okay, it's a lot of data. I've just written huge data rates, with no numbers. But anyways, I was encouraged to do full-length derivations on the board, so I'll do that. So the wire antennas that will operate in Birr, they sample the electromagnetic field 200 million times a second, 200 megahertz. Let's say you save every one of those numbers as a byte. Right. Now there's two polarizations. There's 96 different antennas, and there's 2 times 96 of each type, and then there's what, 54 stations in Europe. Okay. What's that? I don't know. Let's see. That's about 10 to the 2, 10 to the 2, 2 times 10 to the base. A byte is 2 to the 3 bits, so we got 2 to the 5 times 10 to the 12 bits. So 32 PBPS, right? That's the bandwidth you need to record the information. Now yeah, you know how big that is, right? So I happen to know that in 2022, the bandwidth of the world, of the entire internet, is just approaching 1,000 terabits per second. So you need 3% of the internet of the world to capture this data. So it's, and a higher fraction of the internet of just Europe. Okay, it's big data, right? And that's per second, right? How long? So in a year, how much do we get in a year? So there's pi times 10 to the 7 seconds in a year, as you know. So that would be pi times 32 to the 100, 10 to the 19. That's 10 to the 21 bits. What's that? A yotta bit? Is it? I don't know. It's a crazy number. A yotta bit is a lot of bits. It's a lot of data, right? So we can't store it. And this thing works 24/7. Doesn't matter if it's raining, snowing. It's not like optical astronomy. You do this all the time. And the telescopes are, they're so robust. That telescope I showed you was built in 1957. It still works. It's fine. So these things last for ages. So if you imagine you're collecting a yotta bit for a century or something, well, what are you going to do with it? You can't. So not only do you have to sort of handle this data, you have to perform operations on it, computing operations to find the signals within it. So it's not like you can record some data, stop observing, catch up. It doesn't happen. So you end up having to be basically the best data scientists in the world. And so the best data scientists in the world tend to be drawn to radio astronomy because it's hard and therefore interesting. And this isn't the biggest thing there is. So before I Brexited, I worked on a project called the Square Kilometre Array, it's actually 2 telescopes that are in 2 different places, as shown here. So in the south of Africa and in the west of Australia. The place in Western Australia where it is called Boolardy, which is where that comes from. And so I was project scientist for this this telescope, which is currently under construction now. So I hope it works. And each one of these elements here are, are telescopes, right? And you can see that they're starting to be sort of country and continental scale type things. So the one that's in Australia is like that one there. It's not just a coat hanger. It's what we call kind of like a Christmas tree antenna. But that's basically, if you look closely enough, you'll see that that is kind of the same as a bunch of different sized coat hangers on top of each other, right? That each of them is sensitive to a wavelength that's about the size of the coat hanger bit. And so in South Africa, it's a bunch of dishes. So they're 14-meter dishes, 14 or 15-meter dishes. That was the first one that was being lifted up a couple of years ago. And so for this one, this is the low frequency thing. So this is the sort of the super version of LOFAR. You just need to replace, instead of these numbers, wherever it says 96, you need 256. You need 512 here. The bandwidth is 3 times higher, which isn't stated here. So, it starts to be like, wait a minute, we were already at 3 times the internet there. So you actually can't do this computationally yet. So you have to come up with some tricks. Do I want to show you this? Oh, it's playing anyways. Okay. So when the data comes in, you can do 2 things. One is this, which we call beamforming. That's what BF is. But that just means adding the signals together. So you take your 3 signals and you adjust the delays of the signals in a computer. So you do it electronically or you do it in software, and you add them together. And when you add them together, the thing you get is a stronger signal. Now, usually it's way more than 3, and the signal is essentially invisible until you've added them all together. So that's one option. You can add them together, and then in that direction, you get a time series. But if you have a big computer, you can also add them together in that direction, in that direction, in that direction, and you can make pixels off the sky. Okay. The other thing you can do is more complicated. But it's basically, instead of adding the signals together, you can multiply them. Actually, you correlate them. So you Fourier transform them first. So here the signal is coming down. There's 4 antennas for some reason. It's split into its component wavelengths or frequencies. So we're using a Fourier transform. It doesn't have to be a Fourier transform. There are other ways to do it. So it's split into its component colors, right? And then each of the colors from each of the antennas is taken together. And you multiply the blue with the blue and the green with the green. Eventually. Okay, so you multiply them. And each time you multiply them, you get a dot on this 2-dimensional space. And as the sky moves, can you see the sky moving? The pattern changes, right? And the thing you actually get, that's a real one from a real telescope. That's actually the Fourier transform of the sky. So you inverse Fourier transform it and you have an image of the sky. So that's more complex, but that's how you get an image, a radio image. So you can either add them or multiply them with a few extra steps. And in that way you can get an image of the sky, or you can get a time series of individual pixels, depending on what you want to do. If you do the other one, where you just add them together, that's where I'm interested, because then you can see what's happening across the sky on timescales of nanoseconds. You can see very fast brightness transitions anywhere. And if anything is changing in brightness on these ridiculously fast timescales, it's probably really interesting. It's probably physically quite extreme, and you want to know about it. Okay. If you do this, this is some data from Birr, which I'll come back to. You get some, this is like, I think it's like a minute of data. So about a minute here, and 100 megahertz or something of bandwidth. There's lots of signal in there. Can you guys, you can see this really bright thing, right? This is actually a pulse from the Crab pulsar. It's the brightest pulse the Crab pulsar ever emitted. Well, it's the brightest pulse the Crab pulsar was ever, that we ever saw from the Crab pulsar. And if you look really carefully, you'll notice, oh look, there's another one, and there's another one, and there's a load of them over here. And if you look really carefully, you'll notice there's actually tons of them. And they're separated, they're all separated by 33 point, something precise milliseconds, because you get one each turn of the star. Okay. Right. Okay, so what? I forget what the next slide is. It better be good. Oh yeah, okay. So this is like this is an attempt to show all of the radio sources ever detected on one plot. And that's luminosity, so how bright they are on the vertical axis, which you'll see, this is log. So you'll see that covers 25 orders of magnitude, so it's crazy. And this is the product of how long they last. So if something flares for a nanosecond or a minute or whatever, times the frequency it was observed at. The reason I do that product is so that I can have an uncertainty principle that's a straight line there. Because if you have a 1 megahertz wave, you can't have a nanosecond duration of that wave, right? Because it would be less than a cycle, right? So if you have a 1 megahertz wave, it has to be a microsecond at least in duration. Otherwise, it would be in that gray area that we know doesn't make sense. And there's loads of stuff on this, right? And so whenever we build a telescope, we can say, oh, I want to look over here, I want to look over here, I want to design the telescope to look here. And the pattern that's there, where there's sources and where there isn't, that's where we've looked. So this does not mean there's no sources over here. There are no, so these things here, these vary on milliseconds, right? This does not mean there are no sources that vary on a nanosecond or microsecond. It means we're physically incapable of designing hardware good enough to do it. So we haven't looked. Except we looked at the crab, because we don't have to search for it. We know it's there. We can really focus on it. And the crab does vary on 100 picosecond scales. And at that point, our resolution fails us, and it's probably less than that. So there's a lot going on. Okay. Oh yeah, I'm going to talk about pulsars. Okay, so that is why I have this. This is stellar evolution in a slide. So there's a whole lecture course on this, but this is it. This is all you need to know. So you have, something like you have a molecular cloud there on the left. So this time goes this way. Stars are formed. Stars of various different masses. So on the bottom here, you have a star like the sun. Okay, it's going to be a white dwarf. You have a star like Eta Carinae, which is about 200 solar masses. That's going to be a black hole for sure. And in here you have a star that's Betelgeuse there. So a star like Betelgeuse is probably going to be, it's probably going to undergo a supernova and become a neutron star. Neutron stars that can behave like pulsars. And they're the ones I'm going to talk about. Most stars end up as white dwarfs. Some of them end up as neutron stars, and not really that many end up as black holes. So neutron stars are pretty weird. That's about the size of a neutron star there. Centered on Birr. So they're about, 25 kilometers across, but they're more massive than the sun. You really don't want to be anywhere near them. G, M over R is a very big number. M is big and R is small, so you'd be ripped to shreds if you got anywhere near it. I guess, did it make you do that calculation of the difference in gravity between your head and your feet when you fall into a black hole? Okay, well, you get spaghettified, I think is the term. And that would definitely happen here. But I think it's worse than a black hole because there's so many other things in a neutron star that can kill you. So their temperature is X-rays, well that would kill you. Their magnetic, God help you if you have anything metal on you. They're very strong magnets. They're very extreme on pretty much every measure that you can come up with. This is kind of what they look like. So they emit a beacon of light from their polar regions like that. If you point a radio telescope at it, you'll see a signal like that. Every time it's pointing at you, you're going to see a bloop, bloop. Okay. Okay. If you point, that telescope that I showed in my first slide that was outside my office window, if you point that at the first pulsar ever discovered and you stack the pulses on top of each other, you've probably seen that album cover, right? Joy Division album. Joy Division were from a town called Macclesfield, which is right beside that telescope, basically. So they knew about pulsars. Sorry, they know about pulsars. Okay, so this is so that's what I had there. But here, this is the same kind of data, except I have frequency resolution, right? So one strip across this in horizontal sense is what I showed there with the pulse. But with something like LOFAR, you get like quite a lot of frequency resolution. Okay. Okay, what's good about pulsars? A lot of things are good about pulsars. One is that this rotating signal that I mentioned, it's actually really stable. They rotate very stably. And so you can actually use these pulses that it emits like the ticks of a clock, right? A very good clock. And so the ticks come in like on the left there, right? But if you start to add them up together each time, you just average them, add them all up together, more pulses coming in, add them up, you get this kind of thing on the right. They're a bit, they're a bit variable as they come in individually, but when you add them up, let's say you get to 1,000 pulses where that's got to on the right, you get something very stable, and so that's something you can use as a clock. I know these things can spin in milliseconds, so that could just be observing for like 5 seconds. Right? That means you can use them as a clock. Very, very stable, high precision clocks in very strong gravity are like Einstein's dream, I guess, laboratories. And so you can do a lot of precision astrophysics with this. Stars are often in binary systems, and so if you measure the ticks from the clocks, you'll notice, oh, this thing's doing a Doppler shift, and it's in a binary, and you can measure all these things very high precision. The highest precision thing that you can do in astrophysics. So, for example, this particular pulsar, this is its spin period, right? And that's the uncertainty on that, right? So we're sure about all the numbers down to the 7, right? And so, but to the attosecond, we couldn't swear to it. And if you have things, extremely compact and therefore stably rotating objects, just naturally, nature gives you that, great. And they emit radio waves that you can just detect by building, getting a few coat hangers in the field. You can do extremely precise measurements, and you can study objects that are living in strong gravitational fields, for example. So that's something you could never do on Earth. Right? We have things for detecting gravitational waves, but they're not detecting strong gravitational fields. They're much weaker. Okay, so time behaves differently depending on gravity. If you have strong gravity, time ticks at a different rate. And I'm sure you've heard or you will hear about, you can get a nice atomic clock and you can keep, synchronize it with another atomic clock and stick one in a plane, fly it around a bit, come down. Oh, they're different. Time is different because gravitational potential was a little bit different, or it was a bit further from the surface. Yeah, well, you can forget that. This is like way more extreme. Absolutely, like this is just a gold mine for studying gravity. So not only can you study, compact objects in binary systems and study, you can check to see, well, Einstein's prediction for that kind of orbit is such and such, and you can test Einstein in a way that you could never do on Earth. You can also study gravity in the radiation regime. You can study gravitational waves. So this is what a gravitational wave looks like if it's passing through a person. I've magnified the gravitational wave strain quite a bit, but that's the effect that you're looking for. And so what happens in this case is that you're measuring the time the pulse takes to get you, for a pulse from the pulsar, and it'll come either a bit earlier or a bit later. If a gravitational wave is passing by, and you have a pulsar over there, the signal will be a bit earlier or later. And if you have a bunch of pulsars, you can triangulate it. Right? You can say, oh, there's gravitation wave from over there. And depending on the delay, you can work out how strong the thing that met it was. Okay. And by doing this, you can, you can really do a lot of, gravity work. So here on the left, these are plots of the same pulsar. So this pulsar 19, 16 plus 13, that's just named for its coordinates on the sky. That's two neutron stars that are orbiting each other in a binary system. And they should be, because they have a non-symmetrical mass, they should be emitting gravitational waves. And so if they're losing a bit of energy, the orbit should shrink, right? And so the period of the orbit should shrink each time it does an orbit. And over the course of years, it should shrink by, many seconds. Right? We can measure these things to, very high precision, so we'll definitely notice if the orbit shrinks by 10 seconds. Easy. Each of these red points has an error bar on it, by the way. You just can't see it, it's quite small. The black horizontal line at the top, that's the Newtonian prediction, right? And the blue line that goes through all the points is not a fit, that's the prediction of GR. Right? And so, so some guys won a Nobel Prize for this. Actually, you can see they won the Nobel Prize in 1993, and then they stopped observing it. They just stopped, right? Yeah, okay. They were really trying down here. A colleague of mine looked at it again, and you can see much later. Anyways, GR still works. That's good. Yeah, phew. And so this is doing, you might probably hear about the orbit of Mercury is precessing and stuff at some sort of tiny but measurable amount. This is really dramatic, right? These are very easily measurable things, and this is not the most extreme system we know of now. And so we can do a lot of gravity tests. And so you probably hear about the LIGO system, which is on Earth. So that's basically two long tunnels that are 1 kilometer or 2 long. They fire some lasers up and down, and they measure the time it takes. And did the length of this tunnel change a tiny bit because the gravitational waves went through it? That's the principle of it. So for pulsars, we can do the same thing, except that our tunnel is basically the line between us and the pulsar. It's sort of a galaxy scale. And there's not just 2 pulsars, we know about 3,000. Great. So triangulation is not a problem. Because this is galaxy scale, and LIGO is sort of city scale, the mass that it corresponds to is different. So LIGO sees things that are about 10 solar masses or something, 10, 50 solar masses. Whereas pulsars see supermassive black holes, much more massive things. And there's an intermediate system called LISA, the Laser Interferometer Space. I can't remember what it's called, what it spells. But this is basically a LIGO-like system, but with lasers that's actually just kind of put into an orbit, and that's sensitive in between. Okay, how are we doing? Good? Right. That's pulsars. I spent a lot of time doing pulsars. When I'm not doing them, and when I'm not preparing the hardest galactic structure exam paper ever to have been given in Trinity's history, I study fast radio bursts. This is a fast radio burst. So this is like that green thing I showed from LOFAR. This is data from the Lovell telescope. So just like the Crab pulsar thing, it's just a nice sweeping pulse. There's a reason for it sweeping in this particular way. But because of this delay, you know that this source is from a very, very, very high distance. These things are in fact outside of our galaxy. I'm leaving this up here because it preludes a rant later on. You'll notice that you can see the fast radio burst here, right? You can see it sweeping through, right? This is a signal coming from something at a very large distance, right? Many a megaparsec away. But you can see all the other stuff too, right? Okay. And so these, with the telescopes we build, we can detect a mobile phone on Neptune, right? So if if a megalomaniac decides to broadcast really strong radio waves right at us from, say, a satellite orbiting the Earth, that's really bright. That kills us, right? And we see that a lot, right? There's lots of radio emitted much closer to us than that. All right, that's one fast radio burst. That's another one. That's kind of the most famous one because it was the first one detected. I like this one because, well, I like it for a few reasons. This thing was so bright, it basically broke the telescope. Can you see that after the signal, the data is different, right? So this is actually not done with, so when I said before, we separate the data into its component colors using Fourier transforms. Yeah, that's what we do now because we have fast computers. But previously they did it using analog circuits. And so if you get enough RLC circuits and mix them around, you can divide things into their frequency, make filters. Do they make you guys do that? Yeah, okay. So this is like, so what happened here is that, the data is just collecting noise from the sky, and then this signal just went, poof. The top of this signal is actually flat-topped because it broke the digitizer, and then it goes all the way down, and then the rest of it is the recovery of an RC circuit. So that's what's happening. Like, the data isn't lower here, it's just the RC circuit got broke, and it slowly builds up back to this level after several seconds. And the first time that this data was searched, this was like not seen the first several times this data was searched. We obviously didn't search it by looking at it with our eyes. There were various filters that say, if ridiculously bright, get rid of it. Couldn't be real. Must be coming from right beside us in the telescope. Must be from Evan's phone or some local source of interference because it was so blindingly bright. But thankfully, we look at the data over and over again, and we noticed it. This is another one, just plotted in a slightly different way, not by color. I like this one because, well, I found this one, so I like that one. It's also quite, you can see here, it's less than a millisecond, right? And actually, the resolution here is basically limited by the hardware that recorded it. So we only kind of have an upper limit on it. So this thing isn't even lasting a millisecond, right? But it's really bright. This delay is so large, this is kind of a proxy for the distance. We know that this thing is very distant. So it's very bright if we see it, if we still see it. But what is it? Like, we kind of don't know. So, if you have an idea, let us know. That's not the end, though. We can kind of figure it out, right? So you know this, right? This is very important. You should all know this, right? There's a speed limit that you can't break. You know how you can go 10% plus 2 over some speed limits? And it's fine. You can't break this one. But this is it has a kind of a profound implication. It means that, okay, let's say I detect a signal that lasts a millisecond, right? The last one was quicker than that. But if I detect a signal that lasts a millisecond, it means the thing that emitted it could not be bigger than 300 kilometers in size, right? I didn't get that when somebody told me that first, or I read it first. I had to sort of, I don't think I had a beard at the time, but I had to contemplate it. But otherwise the thing wouldn't be causally connected, right? Which means just is a no, right? So we're detecting things from all over the sky that last a millisecond. That means they're distant, which means they're really bright, but they're tiny. Like, that's way smaller than a star or a planet or a moon or a white dwarf or everything but two things. Right? So there's a neutron star on the left and a black hole on the right, and you can see these are the only things that are left, right? And they're kind of they're around the same size, right? So I said the neutron star is like 25 kilometers or something, and a black hole that was one solar mass would be about 5 kilometers. That's the short show radius. Right? They're not too dissimilar, right? Now, as it happens, there are more fast radio bursts where we can make this even smaller. But it has to be a neutron star for other reasons. One is that the emission is very polarized, which means there's a magnetic field, probably. And a magnetic field would constitute hair in the context of black holes don't have hair, but neutron stars have loads of it. They don't emit things like this, so it really has to be a neutron star. Okay, great. So these things are happening all the time. We can detect them with radio telescopes, and so there's a bunch of neutron stars spread across the universe, signaling us. Well, not intentionally, I guess, but what can we do with it? So what? Well, we can use our knowledge of plasma physics to understand this equation. So the signal here, can you see that that's quadratic? It's not straight. So this is a pulse from a fast radio burst. It has this delay because the refractive index of the interstellar and intergalactic medium depends on frequency. But that is it. You don't have to know about that. But basically, the time delay goes as frequency squared, and the amount of stuff, however much stuff there is, actually it's the number of electrons, the more the delay will be. So if it's a very long delay, that means it has gone through a lot of stuff, which means it's very distant, right? And that's how the analysis works. It obeys this. Yeah, so that equation is, sometimes called the German chocolate bar equation because of, well, named after this, quadratic is good type mantra of these lovely chocolate bars. And so we know from looking at this, we can work out the distance. And they all have this nice frequency squared thing. Okay, so they're very distant, right? They all have like billions of, they can reach to 10 billion light years kind of distances. And so what's that good for? Well, each one of them is telling you how much stuff there is between you and it, right? So it's kind of like telling you, well, there's this many electrons, guy, and we know in that direction where there's a fast radio burst, that's how many electrons there are over there. But these things are going off all over the sky. We reckon there's sort of 10,000 of these happening every day. Now, we don't have telescopes covering the entire sky all day, so we only get a handful. Right? But that's just an extrapolation from that handful and knowing how much of the sky we covered. But if we just catch them all, we can weigh the universe. So that's what they're good for. That's one of the things they're good for. And so, PowerPoint. Yeah, that's what happens when you make a PowerPoint of a keynote. You get a baryon. Yes. This whole astronomers think they're being totally cool by confessing in the first lecture. You don't know what anything is, guys. It's mostly dark energy. You don't know what it is. And yeah, well, anyways, they don't tell you that the normal matter that we know about, so baryons, we actually haven't seen most of that either. And so there's a missing baryons problem in it, as well as what is dark matter and what is dark energy. But the fast radio bursts see all of those. So we can really find all of this stuff. Okay. Yeah, I think this is the rant bit. I mean, the inspiring finale. Okay, I think the future is bright. Right? So with these sort of modular telescopes, they get better. If you get a better computer, you remove the computer that you had before, put in a new one, you can record more data. Because we don't record this data. We don't use all of the information. This is how much data you need to record to get all the information. What we do is we say, how much can we record? And we just do the limits of our computing, and we throw away information. So the next year, if NVIDIA says, "Oh, I have a better computer, guys. You can collect way more data and you can get more information out of the same telescope." So our telescopes get better every year, even though they look the same, because they're getting better in the sheep shed where the computers are, right? They're getting better. The shipping containers getting upgraded, right? So they're always getting better. And the modular nature means you can always add on bits as well. And there's new telescopes being built all over the place. That's good. I mean, thankfully, governments in some places at least are inspired by this kind of literally blue skies research, I guess, cloudy skies research here. And so they're building telescopes all over the place to do this. There are a few, because this is like cutting edge data science, there's a lot of spin-offs. The mission for me, and people like me, is not, oh, well, I wonder what the commercialization application of this algorithm. I don't care about that. I want to find exploding black holes. But for instance, a colleague in Australia was trying to find the radio signal from exploding mini black holes. Right? So Stephen Hawking said, look, or he showed that if there were really tiny black holes, they would just evaporate, right? And they'd go bang, and there'd be a signal. Right? Well, Martin Rees said, oh, there'd be a signal, and it would be in the radio. And so naturally enough, people with telescopes said, I want to find it. Let's have a look. Could be exploding mini black holes all over the place. We are not even looking. And so they had a look. And then it collected loads and loads of data. It wasn't this much data. It was sort of the 1980s version of this much data. And they're trying to look through this torrent of data for particular signals. So they needed an algorithm to dig through it, right? And it turns out the algorithm, anyways, is the same algorithm for the Wi-Fi protocol. And so they invented Wi-Fi as a sort of byproduct of looking for exploding mini black holes. But these kind of things happen when you're doing when you're working at the kind of cutting edge of data science. So that's good. That's a motivator. That's that's one of the motivators, I guess. I'm also motivated by the fact that I know that when I was at your stage, I've seen how many things have been discovered since I was at your stage to what they are now, and I realize a lot of that is because we just looked. We weren't able, or we just didn't look before at that thing, and when we did, oh my God, it was bonanza. The universe is it's crazy. We should just look. And now I think, but we've hardly looked at anything. So that fills me with sort of optimism. However, I wanted to say that more grave. You'll recall this 1 second of data, right? Which has telephone calls, up here. It has various satellite signals. It has things that we've tried to filter out but kind of failed. It has air traffic control radar. It has bursts of emission from car ignitions that are near the telescope. It has unshielded electronics and aircon units emitting radio waves. We have computers that our own computers emit radio waves, right? The clock cycles of our CPUs, they sound a lot like the observing frequencies I'm looking at, right? They emit radio waves. And we tend to drive in cars towards the observatory. They tend to be in the middle of nowhere. So there's farmers with electric fences that emit radio waves. So there's loads of stuff here. Loads of, it's encouraging to me that you can dig out a signal from a billion light years away from amongst that haze of stuff that's right beside you. And you kind of have to. So this is supposed to be the electromagnetic spectrum from 3 kilohertz, and it goes over here, and then it loops back, right? Because it would be just too long otherwise. Oops, and it goes all the way up to 300 gigahertz, right? So it's a big part of the spectrum. And capitalists have said, all right, let's sell the spectrum, right? Yeah, They said, look at those radio astronomers, they look happy. Let's commodify it. And ruin their day. And so they said, all right, we've sold the spectrum. The price is too high for you radio astronomers. But that's not fair. They did give us some protected bands. And you'll see those here as yellow, light yellow. So that one. Not that one, that's dark yellow. And I think that one as well, but that's kind of shared. Yeah. Okay, so the protected, and this was like decided in the 1950s when people thought like 1 megahertz of bandwidth was like insanely large, and 200, And so the radio astronomers don't use the protected bands. They just say, oh, let's use the whole thing. Let's use the whole band, and sure, we just take our chances. If something's transmitting in the band, we just deal with it. Because if we just limit ourselves, we're effectively giving ourselves a smaller telescope. We'll look at it all. We'll look through this haze, and we'll just filter it out, and we'll figure out what it is, because we'll just take on that challenge, because we have to. And that's why this telescope, so the SKA telescopes, so you notice where they are, but now, like, these are actually in places where there are no people, or very few people, right? And so, like, especially the Western Australia site, the population density here is something like 5 per Belgium or something, It's like, it's really, there's not many people, right? And the people who live there, like, they might have their own plane, because there's like, you can't like walk or drive anywhere. It's really remote. And if you observe the sky there, you don't see these transmissions. You don't see all these transmissions. And we're basically going there to hide from people, right? And so to get a radio telescope and put it on top of the SNIAM, you see a lot of radio transmissions from Dublin. We just put a couple of radio telescopes on top of the SNIAM, by the way, making a new lab experiment, which you guys might see. That's a bit of fun. But if you want to see, very tiny voltages induced in the wire from something 1 billion light years away, and you're right beside, a city or even a town, or even a little village like Birr, you have a lot of interfering signals in the way. So one strategy that radio astronomers have been using for a while is run and hide. And these are the most pristine, and the mountainous region in China that has the big dish is another example of that. And that's in a valley between, with mountains surrounding it. And those mountains block signals, right? But these are the quietest places you can go in the world. And just when we design telescopes and start building them, we realize you can't run from satellites. And then you think, oh my God, is somebody intentionally putting satellites and aiming radio signals intentionally at remote places? And are they slightly richer than us? That means they might win, right? So, actually, I heard a great example of this in the last year about the run and hide strategy. So there's a couple of radio telescopes that are being designed and constructed now for deployment on the moon, on the far side of the moon, not the near side of the moon. The near side of the moon is really noisy from radio waves because it gets loads of signals from us. We're not very careful when we transmit television or radio, commercial radio signals around. Just fire them around anywhere. Hits the moon and bounces back. Who cares? So you have to go to the far side. We're at the point now, thanks capitalism, that we have to go to the far side of the moon to have a radio quiet environment. But don't worry, because as of next year, there will be 4G on the far side of the moon for real, to prepare the area for future human missions. I don't know why they can't just have cables. There'd be a lot cables from the far side to the near side. It would be much simpler than the mad. So it's a Bell Lab, Nokia kind of NASA project to it's a big. I would have thought cables would have been kind of easier, and they wouldn't be transmitting radio waves. So it's kind of, you know, anyways, I'm a little bit worked up by it. So a colleague of mine who is way more worked up about it than I am, actually, has this table that he keeps updating, upsetting himself with. These are a bunch of satellites that are either orbiting or planning to be orbiting the Earth the next few years, because you know, Facebook needs to have more than 10,000 satellites apparently, and I guess you've probably seen some of you might have seen Blue Walker 3, which launched in the last kind of couple of weeks. You know, and these are all transmitting radio waves and stuff. But for real, I mean, I would like, I guess, an ideal world that these things were not transmitting radio waves towards Earth. But I guess in reality, we have to work with these people. But in a way, I guess it's the same challenge, because we have local terrestrial sources of interference that we just deal with them. We don't know how to do it now, but we figure it out. We just have to get cleverer at our data analysis, and hopefully we can do it. And in fact, we have to do it, because if you're finding signals from, if I'm telling you this pulse over here has come from a neutron star 1 billion light years away, and I think it's, you know, 20 kilometers across, I think it's this bright, and I think it has this magnetic field strength, then you want me to also be able to say, the 75 other signals in the data, I know what they are. That's from that satellite, that's from that, that's from that. You don't want me to be clueless on that, right? So it's sort of necessary. It's necessary for the scientific method. Okay. I'm going to leave it there. Thanks for listening, guys. So I said thanks, and anyone has any questions, which is probably.
Just for the South Africa capsule,
Yeah.
is there a reason why there is spiral?
Yeah. Let me just, I'll just get it up again. Yeah, they're in a spiral shape, and you'll notice the spacing along the spiral arms increases as you go out. And so it's not because somebody who likes spiral galaxies designed this. There's a good reason for it. But I might need chalk to explain it. So if you have just 2 telescopes and you add them together to make sort of 1 telescope, then that's great, but you only have the ability to see at one. I'm try and draw it. That kind of very close. Okay. So there's some wavefront coming in here, and these are separated by distance d. Okay, and this is supposed to be lambda. Right. And so you have a resolution on the sky which is lambda over d. Right, where d is the distance between the points, right? And it's actually this, you know, lambda over d squared, if you wanted to square degrees. And there might be a 1.22 in there or something like that. Depends on the optic, depends on the shape of the dish. But that's great. That means you only see things that are that size. But you want to see things that are finer, right? And you want to see things that are bigger. So if you want to see things that are finer, you only need to make d bigger, right? You put another telescope here. And now you have a resolution of this one, d prime. Right? And you also have this. And now you also have this as well, whatever that is. And if you put in a 4th telescope, you'll find that you get 4 times 3 divided by 2 pairs. N over 2 by n minus 1 pairs. So that's why you have loads of different ones at different scales. You get resolution on different scales. So the really far away ones let you, like the ones that are here, and the ones that are on the edge, they let you zoom in your image. And the ones that are close by give you the bigger structure. And if you do a logarithmic spacing along the arms, that's the optimum way to choose these different values of D. Yeah, so it gives you the nicest image, basically. The one in Australia is also supposed to be spiral arms, right? It's supposed to be three spiral arms gives you a lovely image. You can do it with 5 as well, but you know that means there's less per arm, and you know there's a kind of a balancing act. Also because you only have so much money to build so many telescopes. But the one in Australia is also that way. But you know, there's like a river there and mountains and stuff. So it's basically as close as possible to a spiral arm given the terrain. I know it looks like a pretty messy 3-spiral there, but in the statistical distribution of it, it's pretty good. Yeah. Yeah. Yeah, well, the first one is less costly. The second one, so we basically just say we add for, call that viewpoint. I'm not really sure why we call it that. So I think another is a correlation. That makes an image. And this is way more costly computation. However, what we do really is we do beamforming a lot. Right? So if there's something in the sky over here, let's just say should only have 2 arms, right? Let's do this, you know that. If you have a telescope here, and you want to do a beamforming, what you get is sort of a pixel like this. So you see everything here. So that's what you do when it's beamforming. If you do an image, you just get an image of this kind of area. But what we do is we say, oh, well, that's no good. We just have 1 pixel. So I'm going to form another beam here. And actually, I'm going to form another beam here. And you end up doing as many beams as there are pixels. You end up doing basically the same kind of computation. It's just you get time information from this lateral. And you usually just do it until the point where you have no more computers left. But like by its nature, this is more challenging. More operations. Yeah. As opposed to a radial line.
Well, like if you like for example, some radius and then radial lines, so wherever you just follow, that's appropriate.
Yeah, I think yes. I don't know,
You were saying there was between ones, there's so many that you have like different current ones, like you would not have to have them.
yeah,
And you're saying that like current arrays, they just throw what's into that, right?
lots of
So what's the benefit of having that many extra ones? Like if it's still more accurate,
yeah. So you're saying if you're only going to use this much data, why do you collect this much and then get rid of it? Why don't you just collect this, right? There is a benefit to it because when we collect this data, we do a few operations to the data that mean it's much better to then do the operations first, then throw it away and keep this amount. That it's much better than just recording this. So we keep some of the benefits of the resolution. Yeah, if there was no benefit to it, we wouldn't do it. Yeah.
I just thought of you showed this like a few with either part. With the low band antennas, we have focus organized, but the high band ones are using that.
Yeah. So the low band antennas are kind of randomly oriented, but the high ones are very structured. There's a few reasons for that, and some of them come down to for the high band. Basically, the question is why the high band one's structured, right? Because that does give you some weird features in your imaging. But there's some practical reasons for like, how you can lay them out. It's just practical infrastructure reasons that overrides it for the high band antennas. But they are, between Birr and the other stations in Europe, there's a randomization in that scale that sort of helps to cancel it out. Yeah. I mean, we do have to factor in like a bunch of practical stuff. It isn't sort of the mathematical option. You good? Sufficiently bamboozled?
Okay, well,
Okay.
I want to say
Thanks,
thanks
Aaron.
for coming, and yeah, a little gift from what's here to say thank you, because
A gift?
yeah, because
Chocolate, my weakness.
Little thank you gift for giving
Oh,
us
thank you
all.
very much. That's great. Oh, we're done for free. Yes. Thank you. Thank you very much.